Hello, welcome to Electrical Circuits part number 11, Parallel Capacitive Circuit Analysis. If you remember from part 10 on our purely capacitive circuits, we flip-flop some of our formulas between the series and the parallel. So rather than using the reciprocal formula, we'll be using the additive formula here. So our total capacitance is equal to C sub 1 plus C sub 2 plus C sub 3. So we take our 50 microfarads plus our 75 microfarads plus our 20 microfarads, giving us 145 microfarads. Now we'll be looking for our reactances. So X sub C1 is equal to, and we'll be using the formula 1 divided by, open your parenthesis, 2 pi frequency times our capacitance, in this case C sub 1. So we'll take our 1 divided by, open parenthesis, 2 pi times our frequency of 60 times 50 microfarads, giving us 53.05 ohms. C sub 2, we use the same process. We just specify the capacitance of the second capacitor in line, and which would be 75 microfarads. That'll give us 35.37 ohms. X sub C3 would be equal to the 1 divided by, open our parenthesis, 2 pi times our frequency times our capacitance of the third capacitor. So it'll be 1 divided by 2 pi times our frequency is 60 times 20 microfarads, giving us 132.63 ohms for our total capacitance, or for C sub 3. X sub CT is equal to 1 divided by 2 open parenthesis 2 times pi times our frequency is 60 times our total capacitance of 145 microfarads, giving us 18.29 ohms for the total circuit reactance, capacitive reactance. Now we'll be looking for our voltage drops, and because the values we was given at the first, we had our total VARs, which replaces total power. VARs, volts, ampere reactances is what we use here. It takes in consideration for all three. Remember, it's also known as wattless power. And so for our V sub T, for our total voltage, we have to do a little bit of a twist. Instead of using the Ohm's law, it is basically Ohm's law, but because we're having the power, we're having to use one of the 4 wheels, one off the big 12 wheel, and so our total voltage will be equal to the square root of, open the parentheses, VARs times our X sub C total. And so we take the square root of 787.08, that was a given value to us, times our calculated total capacitive reactance of 18.29 ohms, giving us 119.98 volts. Now remember, in a parallel circuit, our voltages are constant across all branches. So V sub T is equal to V sub 1 is equal to V sub 2 is equal to V sub 3. So we can go ahead and populate that same 119.98 volts for V sub 1, 2, and 3. Next, we'll find our current drops at the individual components and also the total current. And so I sub 1, and we're back to using straight up Ohm's law. I sub 1 is equal to V sub 1 divided by X sub C1 in place of the resistance. So 119.98 volts divided by our 53.03 ohms at the first capacitor, giving us 2.26 amps. I sub 2 is equal to V sub 2 divided by X sub C2. So 119.98 divided by 35.37 gives us 3.39 amps. X sub 3, I sub 3 1 is equal to V sub 3 divided by X sub C3. So 119.98 volts divided by 132.63 gives us 905 milliamps. For our total current, we'll simply divide our total voltage by our total capacitive reactance. 119.98 divided by 18.29 gives us a total of 6.56 amps for this circuit. Now all we have left to do is our VARs sub C1, VARs sub C2, and VARs sub C3. And now we can use, since we have our currents, we can actually use one of the easier formulas and of the main ohm law. And so VARs sub 1 is VARs sub C1 is going to be equal to I sub 1 times V sub 1. So we have current of 2.26 times our 119.98 volts gives us 271 VARs. VARs sub C2 is equal to I sub 2 times V sub 2. So 3.39 amps times our 119.98 volts gives us 407 VARs. And then last, VARs sub C3 is equal to I sub 3 times V sub 3. So we take the 905 milliamps, put it back in standard decimal notation, times our 119.98 volts, giving us 109 VARs. Here's all of our calculated values listed out. These are the expected values, what we should expect to see when we go make our live readings with the meters, with our meters on this circuit, and compare, is it close, if it's somewhere in the ballpark, then we need to look somewhere else. If it's not within the ballpark, is way off, we need to look a little bit closer. That concludes part 11. Thank you.